It's now time to discuss the most dangerous equation in general chemistry. I say dangerous because this equation is probably responsible for more errors on quizzes and exams than any other. It's called the Henderson-Hasselbalch Equation, and it's very useful if you keep in mind its limitations for determining the pH of a buffer solution if you're given the concentrations of the conjugate acid and conjugate base. We're going to derive it now, and in doing that, we want to take a look at our equilibrium constant expression for a weak acid in solution. Now, one of the things that we saw when doing calculations with buffers was that it was sometimes the case that the amount of HA lost and A minus formed over the course of the reaction was quite small. And as a result, the otherwise potentially complicated quadratic math here really simplified quite a bit. Henderson-Hasselbalch is making those same assumptions. So let's start by taking the negative log base 10 of both sides of this equation. Doing that will bring us to pKa and the negative log base 10 of our equilibrium constant expression. Looking at this at the moment, you may be thinking to yourself, well, this hasn't really helped any, has it? However, there's something in this equation that's quite interesting, and that's this. Negative log base 10 of our H plus concentration is how pH is calculated, and that appears to be in this formula if only we could pull it apart. To pull this apart, it's important to remember one of the useful properties of logarithms. That property says that things that are multiplied inside a logarithm can be separated as the addition of two separate logarithms. Let me demonstrate. In this case, that would mean that the pKa is equal to the negative log base 10 of the H plus concentration minus the log base 10 of our A minus over HA concentrations. Now we're starting to get somewhere pretty useful, because this, of course, that's pH. We can do one more thing. If we were to move this component over to the other side, it's negative, so we would want to add this to each side of the equation. The result would be the following. That is the so-called Henderson-Hasselbalch equation. And you can perhaps start to see its immediate benefits. If you know the pKa of the acid, and you're given the concentration of the acid and conjugate base, you could plug them into here, potentially without ever doing an ice table. However, that's only true if the approximation that these amounts change very little when they reach equilibrium is true. And as you recall, that's not always the case. You can also get into trouble if those concentrations are very low, because at very low concentrations, the buffer won't be strong enough to control the pH of the solution. In essence, the autoionization of water will be more significant. Both of those approximations can be taken into account with a good rule of thumb. That rule of thumb is as follows: that this only works if the concentration of both the conjugate acid and the conjugate base are 100 times bigger than the Ka. In those cases, you can be fairly confident that the amount lost will be somewhat small. So, in essence, we need to have these amounts be both similar and large. If they're not, this equation won't work correctly. That said, this is a very handy equation in a variety of circumstances where you want to get an idea of the pH of a buffer.